So welcome back. Now we are going to start with yet another chapter, completely different. So it's a change of topic, which is good for the brain to switch once in a while the focus. So what do we have so far? What we've done? We have this standard inverted index. That is the fundamental building piece of any information retrieval system. And now you know why it's called standard, right? Because now we have plenty of non-standard extensions, like we have the byword inverted index, we have the permuterm index, we have the k-grams index, we have the mirrored index. So now you know all the variations of that index, either with the posting list or pointing to the terms. You know now that all the left part of the standard inverted index is in fact some data structure that can be a hash-based structure, a hash table, or trees. Trees allow you to do interval search, so we actually love trees. You saw how for wildcard queries, how it was so important to be able to search for an interval, right? So this is why B+ trees in particular are very popular. We saw how to be tolerant with the retrieval. We know how to have wildcard queries. We know how to do spelling corrections. So for wildcard queries, we use the mirrored index. We use the permuterm index, the k-gram index. For spelling corrections, we use the k-gram index with the Jacquard coefficient. We use the edit Levenstein distance, the one I messed up, had to explain again, and then the Soundex algorithm, right? So these are many techniques. And again, it's really like a cookbook. And when you build a system, it's up to you to pick what you prefer. Sometimes you can even improvise and have some variations of that. But this is basically the knowledge body of what people have been doing in the past. Okay, so the permuterm index is by adding this dollar. Never forget the dollar, right? And then you rotate the word like this on the left. And the k-grams is you add a dollar at the beginning and at the end. Then you have this sliding window of size k. And again, k, when it's 2 or 3, we don't say 2 or 3, we say bi or tri, like bigram, trigram, and so on, byword, tri-word, and so on. There are even these all English words, right? You know, like you don't say 2 times, but you say twice. And it turns out that 3 times, now we say 3 times, but back then we would say thrice for 3 times. I think there is this old word that also exists. All right, so 3 grams. Then we have the edit distance, right? How to compute the minimal number of edits. We have the Jacquard coefficient, which is not a distance, because again, when it's equal, it's a 1. I think there are people who define the Jacquard distance. So there are proposals over there to turn it into a distance with some magical mathematical formula. And the Soundex encoding, which allows us to compute a fingerprint for every word in English. That only works in English. Okay, so this is what we have so far, right? We've already done a lot. It's the 5th week already. And now I would like to zoom out and then back in on how we built the standard inverted index. Because what you had was a programming exercise, you built it. It was small enough that it just worked, right? You don't have to think too much about performance. But we need to think more about performance because in reality, we can actually have a very large collection. So how do we improve on performance? Well, you're computer scientists, so that's going to be real quick. You know that the brain of the computer is the CPU. Even nowadays, you could argue it's the GPU. But anyway, there's the memory that is basically when you work with the CPU, you manipulate things in memory. But if you shut down the computer, it's all gone. Then you have the disk that's also called persistent storage. So that's the part that you keep when you switch it off. But on the other hand, it's much cheaper. This is why we still like to have it, but a bit slower. And finally, you have the network where you communicate between machines, right? And so far, we haven't really looked into it because we had a single machine. But of course, if you are a search engine like Google or Bing, then obviously you want to consider the network as well. Well, I'm a database person, so I'm not so much into hardware, but I do have this abstracted view on hardware. All I care about as a database researcher is the CPU, the memory, the persistent storage, and the network. These are the 4 things that I care about. And in fact, this abstraction level is often enough to do anything related to big data. You don't need to understand the specific details of what's inside. I'm very impressed. I mean, I have hardware researchers, colleagues who know everything about what happens there, and it's very impressed the complexity of what we managed to build. All right. So now, if we look closer into the hardware that is going to be used to build the standard inverted index, I can look at what I can store on one dimension. It turns out that it's the same order for many units of measure. For example, you can consider that the ones at the top are volatile. So this is what it means when you switch it off, it's gone. And the other ones are non-volatile, the disk and the storage on tape. It still exists, the storage on tape. There's still, ETH still backs up all your working directories on tape somewhere. And it matters for durability because you do want to keep the data for longer. Now, as you know, the CPU cache is super fast, close to the CPU. The memory is a bit slower. The disk is, again, a bit slower. And the tapes are even slower because here you even need to send the robots to get the tape, right? So it might even take minutes or hours to start reading. Then in terms of cost, as you can imagine, faster means more expensive. So the cache is extremely expensive per byte. I mean, per byte, of course. So the cache is very expensive, more than the memory, more than disk. And here also SSDs are more expensive than HDDs. And then the types are super cheap, which is why we like them for backup solutions. Now, if you look at what happened historically, to understand the way we need to think about this, we cannot solve this in the same way today as we would have solved it back in the 60s, because some things have changed, in fact. So I'm going to explain that to you in terms of 3 factors. I love to tell that story probably in every lecture that I give. So the capacity is how much we can store. It's the capacity of your hard drive. Then we have, for example, if you take a book, that's the number of words in the book, 600,000 words. My second dimension is the throughput, meaning how fast can I transmit data, the number of bytes per second that I'm able to read or write to the disk. In the case of the book, you could imagine that you can read 1,000 words per minute. I think that even might be a lot for a human being, but it's just around this. And then finally, the latency, which is the time you need to wait until you start receiving the data. So that's for the disk to rotate until the lecture head, the reading head is exactly at the right position. Right? Some people use latency not as when you start receiving data, but when you finish receiving data, right? There are 2 conventions. But in that case, I mean when you start receiving the data, right? So the waiting time. So in the case of the book, it's for you to stand up and go to the bookshelf and take the book, the latency, find the page. This is the progress that these three factors have had over the course of the last maybe 70 years now. I think this is a comparison I run with the IBM Ramac 350 of 1956, which was that enormous, and it could store 5 megabytes, which was at the time very impressive, all the way to now. I think I picked some 30 terabytes drive, Ultrastar. I don't remember the exact code, but the largest single drive that I could find today, 30 terabytes. And then I looked at the specifications of these computers, and I compared the capacity renormalized per unit of volume, because we need to take into account that it's now much smaller. I looked at the reading, so the transfer the transfer speed, right? How many bytes per second can you read? And the latency of the system. This is what I got. And it's actually all in there. The capacity is that, and the throughput relative to the capacity is really that. That's the evolution factor. That's by how much it actually improved. And the idea is that the capacity per unit of volume increased so massively in comparison with the speed at which we can read that we have a huge problem. We store enormous amounts of data, but the time it takes us to read it entirely keeps increasing. And this is really scary to a point that is really scary. So we cannot even manage that anymore. And this is what leads to the whole big data and all the techniques, MapReduce, Spark, and so on, that we need to develop. And so that will have an impact on how we build a standard inverted index, because of course, when you want to index the entire web, then you do have the problem that you have the entire capacity that explodes, but then the speed at which you can produce it is just too slow. So we'll see that you cannot do it with a single machine anymore. All right, then in terms of capacity, this is what it looks like. The cache can have a few megabytes. The memory, as you know, can have a few dozens of gigabytes, even though in data centers, you will find all the way to 4 terabytes and more. The disk, typically, nowadays, what you buy can have around a terabyte. The write part keeps increasing. I could even have put 30 in there, even though it might be rare. And then the types can go in a very, very, very high range, right? Here, I probably meant with petabytes, not a single tape, of course, but the entire facility. In terms of latency, the cache is nanoseconds, the memory 10 to 100 nanoseconds. That's just the order of magnitude. The disk 10 milliseconds, the tapes seconds, minutes, hours, depending on where it is. And then the throughput. 1 terabyte per second. Well, I'm not saying there is actually a terabyte transmitted, but this is just because we look at an entire second, right? Of course, in the cache, the lengths of time considered are much shorter. Then the memory, 10 gigabytes per second, the disk, 500 megabytes per second. For HDDs, for SSDs can be a bit better. It's only an order of magnitude, right? In practice, it's going to be less. And then the types, even less, 200 megabytes per second, maybe. So it's good to know the order of magnitude and also to know a bit physically why this is. So the reason for the latency is really that in these mechanical drives, magnetic drives, you really have these rotating parts, and then you really need to rotate them all the way until it reaches the reading head. So this is what causes the latency. Now, why is that important to us? Well, it's important to us because when you read from disk, you need to consider what quantity you are reading. If you're just reading one single byte, then you're going to just keep waiting until you reach it. And then in relative terms, the time you spend transferring is much slower, right? You wait for the rotating head, and then you just read 1 byte. That's the reason why we actually don't do that. We never read byte by byte from the hard drive. Instead, what we do is we read in blocks. So a typical size on the file system of a block is probably 4 kilobytes. So here I put the order of magnitude of 64 kilobits, depending how you measure. But this is the order of magnitude of the size of a block, right? Typically, you think of a few kilobytes. And when we read or write from a disk, we always read with that quantity. And that means that if you read a block at a time, then in relative terms, you're going to, again, spend more time on the actual transfer, and then the latency is going to be less. But again, this is because you rotate the disk just once, and then you read an entire block, right? So it's more efficient. So this is one of the ways that we deal with the latency issue. And the issue is increasing because the latency hasn't really made so much progress in all these decades, and the throughput has progressed more. So we also have a problem between the throughput and the latency. Blocks are the answer. We just read and write in blocks. And by the way, this is why we have the B+3 structure. The idea of the B+3 is to be able to read and write in blocks to and from the disk. Then you can also cache. That's another optimization technique. You don't put everything in the disk right now. You can keep it in memory for a while and then only choose to persist it to disk once you are done. You can also keep it in memory in case you want it to read it multiple times. So this is called caching. Now you might have the issue that you spend your whole time reading and writing from the disk to the point that the CPU is not actually fully used, which can be a common problem. And in that case, what you can do is use compression so that you compress what you have on disk into less bytes. And then that means that you have less bytes to read, so it's faster. But then the CPU needs to decode and encode, right? To decrypt and encrypt. But that's okay because it was idle anyway, right? In the end, what you want to find is a balance between the CPU and the disk that both are kind of loaded in the same way, right? Then it's a good balance. Okay. But the compression, I'm leaving aside for now. We will spend the next lecture talking about compression, right? We'll just do one kind of compression before we get started, which is the term ID compression, right? So if we look at the standard inverted index, right now, this is what it looks like. We have the terms on the left, we have the pointer to the postings list, and we have here again the document frequency. That's the special one in purple, and I wrote it in black so you barely see it to really distinguish it from the posting list. Now I'm going to time travel. I'm going to go back in time and look at before we actually get the index, how we arrived to that index. Do you remember that the name for these rectangles here is posting? More exactly, it's a non-positional posting. It's kind of posting. Do you remember that it's not just the document, it's a pair with the term and the document? So in fact, if I rewind a bit, it would be more accurate to display it in this way, that I replace the one with ETH1, ETH2, ETH3, you know, in this way. Just to remind you that originally these postings are actually pairs with a term and a document. But you do realize that what you have on the left on the pair is the same on every row. So that's the reason why you just get rid of the term on the postings, right? But technically it's there. So originally the postings are actually pairs. Now, if you continue to go back in time, so this is when they are nicely organized term by term, but before they were organized term by term, before that, they were all over the place, right? Perhaps manipulated in memory in some way, but we basically have this huge set of term document IDs, term document pairs. If we rewind a bit more, it's like, you know, looking at a baby and going back and back and back and back and back in time, all the way to the embryo. So this is what we are doing here. Before it was all over the place in memory. Maybe it was document by document, because when we read the collection, it was document by document, right? So we have ETH, computer data information in document 1, and so on. And even before that, the actual documents where we even have the number of occurrences and the order in which it appears. So this is what happened if we time travel the whole thing. And it is this process that we want to now optimize and scale. But you might have noticed that as part of that process, there was this intermediate representation, consumes a lot of space. Why? Because it's always the same terms, and that takes a lot of space to actually put the terms in there. So there is a first trick that we use in some of the algorithms to construct. It's called the dictionary encoding also. The idea is that in the same way that we have document IDs that are integers, we are introducing term IDs that are integers, right? So I'll explain that next time. The idea is that you replace the term, instead of having the terms, you replace them with IDs like that, T1, T2, T3. And at some other place, you have this dictionary that says, okay, T1 is ETH, T2 is information, and so on, right? So this is the notion of term IDs that we are going to use to optimize a little bit, right? And the idea is that you can do a few computations that are done in the book. They actually took a specific collection. There was 1 gigabyte of text, 800,000 documents, 100 million tokens when they actually cut the documents into the tokens. And then if you assume that a term is roughly 10 bytes in average, the document ID is 4 bytes, then it means that if you take all of these term document ID pairs, in the wild, it was 1.4 gigabytes. Right, 14 bytes in average per each, multiplied by 100 million tokens, gives you 1.4 gigabytes. And so it means that if you have 16 gigabytes, that's basically the total size of the working memory. Imagine your laptop is constrained by a working memory of 16 gigabytes. Then it means you're going to fit 1 billion and 100 million tokens in your memory. So it means you could technically build a standard inverted index for 11 gigabytes of text, right? You can take Shakespeare or whatever, plenty of them, up to 11 gigabytes of text. This is what you're going to fit in your memory as term document ID pairs if you have 16 gigabytes of memory. Now, if you do this compression with the term IDs, and you have, again, this to decode the association between the term IDs and the terms, now you redo the math. The term IDs is just an integer, let's say 32 bits, so it's 4 bytes. Now the size of the pairs, it's no longer going to be these 14 bytes, now it's 8 bytes, that's less, right? So now, if I have 100 million tokens, it's only going to take 0.8 gigabytes instead of 1.4. Now, again, imagine I still have my good old laptop of 16 gigabyte of RAM. How much text I'm going to manage to index now? How many term ID, document ID pairs, right? And I insist on term ID, document ID pairs. Now, if you do the division, you can fit 2 billion tokens in your memory. And now I can actually index a collection on 20 gigabytes of text. Do you realize what we did? With the same machine, the same laptop, the same machine, I could increase the size of the collection that I want to build an index on, right? It went to 11 gigabytes. Now I can process 20 gigabytes. That's what we get with term IDs instead of terms, right? Okay, now it's exactly noon. So I'm going to free you and let you go grab your lunch. There is a graded quiz. It's graded, right? This week. So you have 1 week to complete. Take your time. Do not rush into it. You can also ask any question to the TA team if there's anything. Enjoy the exercise session. And next week, I'm going to explain to you how we manage to go even beyond that and scale up the indexing. Thank you very much. See you next week at 10 a.m.